Hello there, Mr. Sutton here, bringing you the Pre-Cal Honors 9-3 lesson on algebraic limits, specializing in polynomials and rational functions. In this one, we will be finding limits of polynomials and rational functions. We're going to do this algebraically without needing a graph. For our warm-up, because one of the big tools we use in algebra is the idea of plugging in, we're going to explore the relationship between plugging in and limits. So pause the video and using these graphs here, see if you can figure out f of 2 and limit as x approaches 2 for each of these functions. And then see if you can conclude something about what this tells us about when plugging in actually gives us the limit. All right, let's see how that went. So f of 2 for this first graph, that's just our function value at this solid dot, which is 3. And then the limit as we approach this x value from the left and the right also is 3. So the function value and limit matched on this one. For this next one, the function value does not exist because we've got a hole there at 2. The limit, though, as you approach 2 from the left and the right, is still going to be 3. For this one with the asymptote, the function value does not exist. And the limit, I mean, you could call this positive infinity if you wanted, or we could say does not exist. Over here, for this one, the function value is actually this little solid dot up here at y equals 5. The limit, however, as you approach from the left and the right, is down here at 3. And then for this last one, we have a function value at this solid dot at 4. But the limit, as you go from the left and the right, you see they don't actually match, so there is no limit because we have a mismatch there. So what does this tell us about the relationship between plugging in and finding limits? Well, over here on this continuous function, we ended up with the same function value and limit, because if your function's continuous, then where you end up and where you're going end up being the same thing. So in general, we can conclude if a function is continuous at a spot, plugging in is going to give us the true limit. Now, what about if you have one of these other cases with a hole or an asymptote? Well, in that case, plugging in is going to give you undefined, and it's not really clear whether that means there is a limit, like with one of these holes, or there's no limit at all, like with one of these asymptotes. So plugging in fails for holes and asymptotes, but on the bright side, we at least know something is wrong, and we can maybe do a little more work to figure out which of these cases we're dealing with. And then there's this last set of cases with piecewise functions. Here, we got numbers when we plugged into the function, but those numbers really had nothing to do with the actual limit or even whether the limit existed. So plugging in can actually give us false limits on piecewise functions. So at this point, we're going to come up with a little algebraic strategy based on the cases that we just saw. One thing we know right away is that piecewise functions are bad news. So our strategy here is if the function is not a piecewise function, we're going to do the following. We're going to spend a whole lesson on piecewise functions. But if it's not piecewise, we can start by just plugging in the constant that x is approaching. Because we know right away that at the very least we're not going to get a false value like the piecewise functions can give us. Now, one of two things will happen if you plug in a constant. One possibility is that you get another constant back. If that's the case, then you just found the limit. You had one of those continuous functions. If you get something undefined, then we're going to need to do more work because we're going to have to figure out, do we have a hole or an asymptote? You know, one has a limit, the other doesn't. So here's our first real example. Pause the video and see if you can figure this out based on what we just talked about. All right, since this is not a piecewise function, we're just going to start by plugging in 2, what x is approaching. So plugging 2 into everything, we've got 5 times 8 plus 4, so that's 44. And down here we've got negative 1. So when the dust settles, we can simplify this to negative 44. So negative 44 then is the actual limit of this expression. Now a little bit more about what we did here. It turns out on the AP free response, your final answers don't need to be simplified. If this were a free response, you could have just left it as this collection of constant garbage right here, and you would have been done. The only caveat to this is that you might still need to simplify to match answer choices on multiple choice or to make sure your answers aren't undefined. If this stuff comes out to something undefined, then it would not be acceptable. Here's another example. Try this one out. So plugging 4 in everywhere, we've got 2 minus 4 and 4 plugged in the denominator. That's going to give us negative 2 in the numerator. Denominator, we've got 16 minus 8 minus 8, which actually comes out to 0. So this is one of those cases where you really should simplify to make sure it's not undefined. If you get one of these where you have something over 0 and the something, which I'm calling c in this case, is not also 0, then you've got a vertical asymptote, which is to say your limit does not exist. So DNE is our answer for this one. On we go to this next example. Pause the video and get started on this one. All right, so you probably ran into some interesting things when you did that. If you plug 2 into the numerator, we have 4 minus 4, which is 0. In the denominator, we've got 2 minus 2, which is also 0. So what do we do with 0 over 0? By the way, 0 over 0 is one of many indeterminate forms that we encounter in calculus. There's a bunch involving infinities as well that we're going to see later on in life. But this is the first one we've seen. And the very first thing you should do with 0 over 0 is never actually write equals 0 over 0. Because, as we'll talk about a little bit later, this is mathematically wrong to write this. Part of the reason this is wrong is because this is never actually your final answer. You're actually going to get some kind of number for a final answer, or at least you could get a number. And if that's the case, you don't want to say that that number and 0 over 0 are the same thing. So how do we deal with this situation? The key is understanding what causes this. These are caused by common factors that we could have canceled out. Holes, in other words. If you were to factor this thing out, there's something that when you plug in 2 in the numerator and denominator was giving you zeros in both places. So to solve this problem, we're actually going to factor and cancel out that common factor. Pause the video and do that if you didn't already. All right, so factoring out the numerator, we've got x plus 2 and x minus 2. Denominator doesn't change. And we notice here that we can cancel out these x minus 2's. And if we look back at the original here, the 2 getting plugged into these was what was giving us 0 over 0 in the first place. So where do we go from here? Before we go any further, one thing I do need to point out, and this is called linkage, is that we need to keep writing this limit as x approaches 2 on this problem until we actually plug in a number. Just writing this by itself, it's just a random expression. When you attach it to a limit, you're actually telling people what you're doing with this expression. So we need that limit there in order to communicate mathematically. Keeping that there now, we can write this as limit as x approaches 2 of x plus 2. Notice I'm keeping my limit around. And once you've actually canceled out something, you should try plugging in again. Because this x minus 2 over itself is what was giving you 0 over 0. Without that, maybe we'll get something better. When we plug 2 in again, and again, this is when I'm allowed to drop my limit, when I actually plug the number in, because now this is a function value, not just a limit. This is going to give me the number 4. So that ends up being my limit for this thing. So there was a lot going on that last example. Once you feel ready, pause the video and try this one out. All right, so for this one, I'm actually going to do things a little differently. If you plugged in 4 for all the x's, you noticed that we got 0 over 0 again. But it turns out you actually don't even need to really do that step. It's legal to simplify, by which I mean factor and cancel, before plugging in. And you'll often save a lot of time by doing that if you're good at factoring. So factoring my numerator, I've got x minus 1 and x minus 4. For my denominator, things that multiply to negative 8 and add up to negative 2, I've got x plus 2 and x minus 4. And we see right away that there are some x minus 4's we can cancel out. So rewriting this now, we can write limit as x approaches 4 of just the stuff that's left over here. Plugging 4 into that, I have 4 minus 1 over 4 plus 2. 3 over 6 ends up giving me 1/2. So that's it for that one. In fact, that's it for this lesson in general. One final word, though, and that's that you notice we didn't do any polynomials in this lesson. The reason for that is because plugging in always works with polynomials. There really isn't much more to it. They're continuous everywhere. So if you see a polynomial, just plug in and call it a day. And now we're going to call it a day. Till next time, Mr. Sutton signing off.